Wow, 3 spherical chocolates packed in a straight line. So we can kind of imagine it this way. I probably should have drawn the spheres first. Anyway, these are chocolates. The volume of a sphere is 4/3 pi r cubed. Okay. And then the volume of the box is going to be the length times the width times the depth. So we can figure out that whatever the ratio is of these, whatever the measure is of the actual spheres in here, this is one of the radiuses. And so the length of the box is going to be 1, 2, 3, 4, 5, 6 radiuses, or radii. How about that for a correct plural? The one of the other dimensions will be 2 radii. I should make that. So by 2 radii. And then the other dimension not shown would also be the, the height of the box, or the width of the box, however you want to think about it. That's another 2 radii. Whatever those radiuses actually are. If we multiply 6r times 2r times 2r, we get 24r cubed. So that's the volume of the box before we increase the volume of the chocolates. So let us pretend that we'll call S the 50%, or we'll call S the radius of the big chocolates. And we'll call R the radius of the old chocolates, and that's what we were using up here for the volume of the original box. Radius of small. And so we can compare the volumes of the spheres. And we're looking for the ratio of the big to the small. So 4/3 pi times s cubed, that would be the volume of one of the enlarged chocolates, to the ratio of 4/3 pi r cubed. That equals 3/2. So if you were to cross multiply, this would be that the volume of one of these chocolates is 50% larger than the other one. But by getting all of these things on one side, we can have it just as this ratio. You'll note that this fraction here has all of these parts the same except for the numbers themselves. So, or except for the variables themselves. So the 4/3 pi on both sides cancels out. So 3/2 is equal to s cubed over r cubed. And from here we can actually just solve for s. We multiply both sides times r cubed. So we get s cubed equals 3/2 r cubed. And we're trying to solve for s on its own because we're trying to do like we did here, with multiplying all these different r's together. We're trying to get s on its own. So the cube root of s is, or the cube root of s cubed is s. The cubed root of r cubed is r. But then we're stuck with, unfortunately, just the cube root of 3/2. We don't have to figure that out though, because what's going to happen is that new box is going to be 6 times s, again because there's 6 radiuses with 3 spheres in a row, 6 times s times 2 times s for one of the other dimensions of the bigger box, times 2 times s for the final dimension of the bigger box. So this is going to equal 24s cubed. And now, so this is the volume of the big box. This is the volume of the little box. And now we also know that s equals r times the cube root of 3/2. So this 24s cubed is equal to 24 times this value for s, which is r times the cube root of 3 halves cubed. So if you cube the cube root of 3 halves, you get 3 halves. If you cube r, you get r cubed. And the 24 stays the same because that wasn't having anything done to it. So 24 times 3 halves r cubed equals, running out of room, 36 r cubed. And we're looking for the ratio then of the volume of the new box to that of the original box. And both of these are in terms of r now. So we want new box over old box, or big box over little box. We knew that the old box all along was this 24r cubed. The new box we have converted from 24s cubed into terms of r, which is 36r cubed. And this relationship, when you cancel out the 2r cubed and the 2r cubed things, and then simplify 36 24ths, it is answer choice B, 3 halves.